Hello everyone, I'm Xiaojian from Tsinghua University. Today, I will present our work Crash-Consistent Non-Volatile Memory Express. Crash consistency represents the atomicity of a single operation that updates multiple blocks despite a sudden system crash, such as a power outage. Another vital topic is the storage order. It defines the persistence order of multiple individual operations or transactions. Most storage systems use journaling to achieve crash consistency and storage order. We use an example to illustrate the journaling. The workload is creating and writing a new file. A transaction consists of 4 kinds of data blocks: D, JH, JM, and JC. The host first sends D, JH, and JM to the storage. Then it issues a barrier, such as the flush command, to ensure the blocks in the volatile buffer are flushed to the persistent journal area. Next, it persists the JC to enforce the atomicity of the transaction. After all blocks are persisted in the journal area, the storage systems checkpoint the blocks to their home location. In the face of a sudden crash, the storage system can replay the blocks in the journal area to achieve crash consistency and storage order. Persisting a block mainly consists of 4 parts: submission, block DMA, completion, and the barrier. 2 ordered transactions are processed serially with a barrier in between. We find 2 major issues of journaling. The first is the extra storage traffic, including the extra MMIOs of submission and completion, irrelevant blocks incurred by the device-wide flush, and extra commit record generated by the journaling. They consume the available bandwidth of SSD provided to the host software. The second is the serialization of ordered transactions, which poses long latency to each transaction and conflates atomicity and storage order with durability, increasing the transaction latency. To address these issues, we propose CCNVMe, a generic storage protocol that provides crash consistency, per hardware queue storage order, and high performance. First, CCNVMe reduces unnecessary storage traffic, including the commit record, one flush command, and MMIOs. Second, CCNVMe prioritizes ordered transactions by separating atomicity from durability. Using our proposed F-atomic interface, storage systems can ensure crash consistency and storage order with only 2 MMIOs over the PCIe. CCNVMe is designed as an extension of NVMe atop persistent memory region-enabled SSDs. The left picture presents the traditional NVMe storage stack. The right picture shows the CCNVMe storage stack, which uses the persistent memory region feature of the original NVMe. The PMR can be capacitor-backed DRAM, 3D XPoint, or other persistent memory, and can be accessed directly by the CPU load and store instructions. Atop the driver, we design a no-journal file system which exposes an extra atomicity primitive to support atomic transactions. Applications can also issue raw CCNVMe commands to ensure atomicity. We observe that in the original NVMe, the submission queue and doorbells check the life cycle of each request. To store a block, the host first places an NVMe command in the SQ, followed by ringing the SQ doorbell. Note that at this time, the request is about but not yet to be processed. The storage device then fetches the command and transfers the data block. After the device finishes processing, it places a completion entry in the CQ and generates an interrupt. The host then consumes the completion entry and rings the CQ doorbell. Note that this indicates that the request is completed. Inspired by the NVMe workflow, we decide to let crash consistency and storage order take the free rides of the data dissemination mechanism of the original NVMe. Specifically, CCNVMe places the SQ, SQ doorbell, and SQ head value to the PMR to record the life cycle of all in-progress requests. CCNVMe then transfers the NVMe commands and data payloads in the unit of a transaction. First, we introduce transaction-aware MMIO to send the NVMe commands in a large batch. Second, we introduce transaction-aware doorbell to ring the doorbell in the unit of a transaction to let the requests from the same transaction reach the same stage. The other procedures are kept the same as NVMe. Transaction-aware MMIO is based on the persistent MMIO write, which takes three major steps. First, the host uses CPU store to store the command in the write combining buffer. Second, the host issues cache line flush to flush the commands from the WC buffer to the PCIe load complex. Finally, exploiting the PCIe ordering, the host issues an extra PCIe read to persist the command to the PMR. As the overhead of persistent MMIO is expensive, transaction-aware MMIO is introduced to batch MMIOs of each transaction. The key idea is to postpone the cache line flush and PCIe read. Suppose a transaction consists of 3 blocks. The host stores 3 NVMe commands to WC buffer and issues only one final flush and PCIe read to ensure persistence. Transaction-aware MMIO improves the PCIe access efficiency, as large persistent MMIOs brings higher bandwidth and reduce the overall transaction level latency. Other designs, including transaction-aware doorbell to ring the doorbell once for each transaction, in-order doorbell to enforce storage order, are presented in the paper in detail. For crash recovery, CCNVMe provides non-atomic and out-of-order transactions from PMR and journal area to upper layer systems to handle these unfinished transactions. For example, the file system can discard all the unfinished transactions in the journal area. We report the results of CCNVMe against classic and state-of-the-art systems atop recent Optane SSDs and multi-core servers. We first present the performance of persisting transactions. During the test, each thread persists independent transactions. The x-axis shows the size of data content of each transaction, and the y-axis shows the throughput. In CCNVMe Atomic, the thread ensures only the atomicity but does not wait for the durability. We observe that CCNVMe outperforms its peers significantly. The separation of atomicity from durability further improves the throughput. We conduct the same test by increasing the threads. Due to the reduction of PCIe traffic, CCNVMe prevails its peers when the SSD bandwidth is saturated. Now, we report the application performance. In the legend, the MQFS is our proposed file system that utilizes the crash consistency and storage ordering guarantees of CCNVMe. We find that MQFS significantly outperforms its counterparts. The throughput of MQFS comes close to or even surpass ext4 node joiner that does not provide crash consistency, as MQFS provides higher CPU and I/O efficiency. In summary, we propose CCNVMe to provide generic crash consistency and storage order inside the storage protocol. We conclude that storage systems should separate atomicity from durability and reduce the CPU overhead to fully exploit the high concurrency of modern NVMe SSDs. That's all. Thank you for listening.